Hi everyone. This video gives a slightly more advanced method for finding trigonometric values of special angles, and it uses the concept of reference angles. If you're planning on moving on to higher level classes such as calculus, it would be a really good idea to learn it this way and be able to find them this way. The reason being is you really don't want to be using a lot of your brain energy drawing the triangles. You want to be able to just see these values and quickly be able to put them in terms of a reference angle, put them in terms of sine and cosine, and then just use the relationships between sine and cosine and the other trigonometric values to be able to evaluate these. To do this method successfully, it's crucial that you understand the signs of the trigonometric functions based on what quadrant the rotation lies in, and it's also important that you have the sine and cosine values in the first quadrant memorized. Sometimes you might still want to draw the rotation or even draw a triangle if you really get stuck, and that might be especially useful if you're a more visual person. But again, it will really help you if you can get these in your brain automatically and be able to do it this way for calculus. Let's evaluate the sine of 135 degrees. I know that 135 degrees lies between 90 degrees and 180 degrees, which means it's in the second quadrant. And since the triangle is pointed up in the second quadrant, the sine value is positive. The reference angle is 45 degrees. I find that by subtracting 135 degrees from 180 degrees. And so because the reference angle is 45 degrees, this will be the same value as sine of 45 degrees, and it'll be positive because it's in the second quadrant. So the sine of 135 degrees is the square root of 2 divided by 2. Again, the big advantage of this method is how quickly you can get these values as long as you know the positive and negative signs based on the quadrant, and you know all of the values for 0, 30, 45, 60, and 90 degrees. Next, let's find the tangent of 330 degrees. 330 degrees is between 270 degrees and 360 degrees, so therefore it lies in the fourth quadrant. In the fourth quadrant, tangent is negative because the x and the y value have opposite signs, and the reference angle is 30 degrees. We get that by subtracting 330 degrees from 360 degrees. I use my identity that tangent of an angle is equal to the sine value divided by the cosine value. So the sine value at 30 degrees is a half, and the cosine value at 30 degrees is square root of 3 divided by 2. While this is a perfectly acceptable answer, you're pretty much never going to see it written this way, especially if you're taking a multiple choice test. So since this is a division problem, we'll want to multiply by the reciprocal. So I change this to a half times 2 divided by the square root of 3. The 2's will divide themselves out, but we still have a square root in the denominator, which is not how mathematicians generally prefer to write it. So we'll have to rationalize the denominator, multiplying by the square root of 3 divided by the square root of 3. Therefore, the tangent of 330 degrees is negative square root of 3 divided by 3. Next, let's find cosecant of 240 degrees. 240 degrees lies in the third quadrant between 180 degrees and 270 degrees. Since cosecant is sine's reciprocal, the triangle is pointed down. So in the third quadrant, cosecant will have a negative value, and the reference angle is 60 degrees. We find that by subtracting 180 from 240 degrees. Since cosecant is sine's reciprocal, I know that sine of 60 degrees is square root of 3 divided by 2. Therefore, the cosecant will just be that number upside down. And then we'll want to rationalize the denominator. So we multiply by square root of 3 divided by square root of 3. And that gives us that the cosecant of 240 degrees is negative 2 square root of 3 divided by 3. One of the best things about this method is you don't have to do anything special for the quadrantal angles or the rotations that lie on the x or the y-axis. If you're using triangles, the problem with these angles is there really isn't a visible triangle because the radius is going to lie on exactly the same side as the x or the y value. But with these, all you need to do is know the reference angle, know the value of it, and then you're good to go. So, here we go. Cosine of 90 degrees. That's a value I just memorize. I know it's 0. Boom. Done. Cotangent of 180 degrees. I know that cotangent is cosine divided by sine. 180 degrees' reference angle is 0 degrees. So cosine of 0 degrees is 1. Sine of 0 degrees is 0. I can't divide by 0, so this is undefined. Therefore, the cotangent of 180 degrees is undefined. Secant of 270 degrees. 270's reference angle is 90 degrees, and I know that secant is the reciprocal of cosine. Cosine of 90 degrees is 0. So I have 1 divided by 0, undefined. Secant of 270 degrees is undefined. Cosecant of 270 degrees. Cosecant is sine's reciprocal. The reference angle is 90 degrees. I know that sine of 90 degrees is 1. But 270 is pointed down on the negative x-axis. So I will use the value for sine of 90 degrees, but it's going to be negative. So cosecant of 270 degrees is negative 1. And then finally, we'll find cotangent of 270 degrees. As we said above, cotangent of theta is cosine of theta divided by sine of theta. So cosine of 90 degrees is 0, and sine of 90 degrees is 1. Therefore, the cotangent of 270 degrees is 0. Again, the greatest advantage of this method is it's the same every single time. You think about where the rotation lies in the circle for whether the value is going to be positive or negative. You find the reference angle, and then you just use the sine and cosine values that you know for the reference angle and use that to find your values. This is some of the most important stuff, especially if you're going to take calculus courses later on. You're going to be expected to know these values and be able to find them. This needs to be like breathing when you take calculus, and the fact that it's involuntary and you don't even have to think about it.